Hello everyone, my name is Thorsten Polk and I'm a postdoc at the University of Göttingen, and today I'm going to give you a brief introduction into the Modular Breeding Program Simulator, or short MOPS. For this we are planning to put up a whole teaching series on YouTube, and today I will mostly focus on a general introduction to our framework, and in the next few lectures go into more detail about the individual parts of the tool. This for one means the simulation of breeding programs in R. Next up I will show off our web-based application and show some utility functions in R and how to analyze your simulations. And the last big step, I will show off some case studies to give you some examples of how to potentially use MOPS in practice. So, when it comes to MOPS in general, our goal is to simulate breeding programs. And as you might imagine, modern breeding programs are highly complex by nature. So here we have two quick examples. On the left-hand side, you can see a wheat breeding program that's containing of all sorts of field trials and seed replication periods and selection and all those kind of things. Whereas on the right-hand side, we have a fish breeding program that contains a lot of sibling testing, genetic evaluation schemes, multiplication schemes. So those look very different, and basically our goal in the MOPS is to develop a framework that is able to simulate all sorts of breeding programs you can imagine. When it comes to what we are interested in breeding programs, we first have to think about our objective. So especially for breeding companies, that is usually genetic progress, but also economic efficiency, but other things like maintenance of genetic diversity, or how likely it is to achieve a certain outcome, or the general variability of your outcome is something to consider. To achieve those, there are quite a few ways of doing that for breeders. The simplest is probably to just control the number of animals, plants, or plots to grow. But there are also decisions to make, like how many of those individuals to genotype or phenotype, what kind of mating scheme to apply, what kind of selection technique. Is it necessary to use some biotechnology, so CRISPR or DH technologies, or you name them. And so basically so many other options that I can't list all of them. It's just infinite possibilities in the different breeding programs that there are. So in general, this is just a highly complex optimization problem. When it comes to ways of answering that, I would say the most common thing that breeders tell us is that they rely on their experience. But what we want to propose here is the use of a simulation study to aid the breeder or you in your decisions in a breeding program. There are quite a few other tools that were previously proposed. One very famous type of class is cohort-based and deterministic simulation. One example for this is the software zPlan Plus that was also developed in our working group, that is mostly reliant on underlying quantitative genetic theory. So for example, you could think of the breeder's equation. The response to selection is just dependent on your selection intensity, the heritability, so the share of variance that is due to genetic components, and the additive genetic variance. And basically, you know that when you switch up your selection intensity, you can expect some change to the response. And by that you get, for very simplistic designs, get a good feeling of how certain actions impact your breeding program. So in simplistic cases, I would say this is quite a good approximation. But in general, when it comes to breeding programs in today, it's not really going to cut it. So what we are proposing to do instead is stochastic and individual based simulation, and this is what the MOPS package is all about. So the main part of MOPS is an R package, which is highly flexible in its design. So we are still sticking with this cohort-based design. When you remember those pictures I showed before from breeding programs, they all contained of some kind of cohort structure. But internally, everything is based on individuals. So basically every meiosis and every event of recombination is simulated in our package. Next up, we are providing a variety of pre-implemented functions that should cover most frequently applied breeding actions. So for example, breeding value estimation is implemented in there. We have a variant of single step. We have a variant of optimal genetic contribution, and we allow for genome editing. Next up, we are modeling quite a variety of traits. Mostly we are focused on QTL-based traits and allow for quite a few different architectures, from additive to dominance to qualitative or quantitative epistatic traits. But we also allow for genomic values that are just based on the parents and their inbreeding coefficients. And looking at correlated traits in both cases is no issue for us at all. When it comes to the R package, we have quite a flexible structure that contains two parts. For one, we have some general information, so like the position of each markers in Morgan and those kind of things. And on the other hand, we have individual specific information. So for each individual, we are storing its phenotype, its underlying genomic value, what its parents were, and points of recombination, mutation, and so on to derive haplotypes and genotypes on the fly. In terms of storage, we are just using the haplotypes and genotypes of founders, and everything underlying is using bitwise operations, so in general to be highly efficient. This is also the case for the computational part, and for this we are using the R package Miraculix, which is developed in cooperation to MOPS, which is providing this bitwise storage, but we are also using it for matrix multiplication and those kind of things to save massive computation times here. After your simulation is executed, you have quite a few of utility functions to show off the results of your simulation. So just to give you a couple of examples here, you could, for example, be interested in your genomic gain. So here is an example for the genomic value for milk production, and we see that we start off with like 9.5 thousand liters in the first year, and after 5 or 6 generations of mating, we are up to 10,500 liters of milk. Next up, you could be interested in your inbreeding coefficients and how they increase over time. So in this particular simulation, we started with unrelated individuals, and after 5 generations of mating, we are up to an inbreeding coefficient of 0.05. Another thing you could be interested is genetic variation in a particular marker. So here we have simulated a major QTL in this region, which had a first mutation in generation 100, and as there was strong selection on that QTL afterwards, there were just a few generations to fixate that marker in the opposite direction. And lastly, we could be interested in the economics of your breeding program you have simulated. So here we see that in the first generation we are making a deficit, but based on our breeding operations and our genomic gain, after a couple of years we are making genomic gains, economic gains. And with this, I already want to come to an end of this first lecture. I hope this was enough as a teaser, and I would be happy to welcome you in the next few presentations. And with this, I want to also acknowledge our sponsors, mainly the European Union, which has founded our project IMAGE, and our working group, the Animal Breeding and Genetics Group at the University of Göttingen. And with this, thank you for your attention.